Afternoon, guys. I hope you're doing well. What I would like to do here is to walk you through some of how I got the answers for the in-class practice. Now, while it is typically up to you guys to work these kinds of things, what you don't have is the ability to have me stare over your shoulder while you do something. So I thought it might be useful for me to show you a couple of each so that you can see exactly what my thought process is in doing it. And that way you might have a better understanding of what it is you're being asked to do. So I'm going to go ahead and share my screen so that you can see what we're talking about. Now, this is I'm creating the key for in-class practice 1. Sorry, I apologize. I swear to God, every time I turn on the camera, I start yawning. I'm so sorry. So a lot of the beginning of this has to do with unit conversions. So I've got my exam handouts that I pulled up so that I can look at what are those unit conversions so that I can figure out how to do this. Now, this first one, they're asking me to go from centimeters to meters. The first thing I need to look at is where is centi over here? So I see centimeters, C, is 10 to the minus 2 or 1/100th of a meter. Okay, so what that means is that there are 1 times 10 to the minus 2 meters in 1 centimeter. Or I could do this as 100 centimeters equal to 1 meter. Either one works. I prefer to do it this way, but it is perfectly fine to do it the other way. So what I'm going to do is set this up using this one. Now I know that those two things are equal based on the information that I've been given here. That's how I interpret this table. So if I want to go from 156 centimeters, then I want to put my conversion factor into the next block. And I need to have the centimeters on the bottom so that they cancel and the meters on the top so that they stay. So if I know it's 1 times 10 to the minus 2 meters per centimeter, then the centimeters cancel, and that leaves me with 156 times 1 second EE minus 2. Now, I'm using a TI-34. Hopefully you can see that that's a 34. And what I said was the 1 second EE because that's what I need to enter on my calculator to do this. Okay, so we don't enter it as 1 times 10 to the minus 2. If we were to do that and do a bunch of math with numbers like that, we end up with errors. Okay, so we don't want to do that. The exponent, that EE, is for an exponent. And that for me on this calculator is the second comma button. Okay, so if I do that happy math, that tells me that that answer is 1.56 meters. Okay, so that's how many meters I've got in that number of centimeters. Cool, that's awesome. All right, let's do another one. So 4.87 kilometers to centimeter. So now I need to go from killi to centi. Okay, and I'm going to need 2 conversion factors to do that. So I know that 1 kilometer is 1,000 meters. I also know that 1 centimeter equals 1 times 10 to the minus 2 meters. I only need to use both of those because there's no direct number that I've got here to be able to do anything else. So remember that these are all of your, the prefixes that go along with these units. So we're currently talking about meters and we're talking about centimeters and kilometers. So this is always how we calculate to get back to that base unit, that meter. Okay. So setting up those two, I know that I have 4.870 kilometers. I know that 1 kilometer is 1,000 meters. That cancels the km and leaves me with meters. And then I have 1 times 10 to the minus 2 meters is 1 centimeter. And so the meters will cancel, and that will leave me with an answer that's going to be in centimeters. So 4.870 times 1,000 divided by 1 second EE minus 2. And that gives me 487,000 centimeters. Okay. So this is the kind of process that I'm going to go through every time I want to do one of these calculations. I'm going to do the third one, the ml to ml, because it's a small m to a big M. Okay. So this is a milliliter. So that's small m. So small m is milli. So that's 10 to the minus 3. And the other one that I need is this big M, and that big M is a megaliter. And a mega is 10 to the 6th, or 1 million. So 1 megaliter equals 1 million liters. Okay. So again, I can set that up exactly the same way that I've done before. So I'm going to do the first conversion to take milliliters to meters, and then from meters to megameter. All right. So I take my number 7809. That's in milliliters. I know that 1. Sorry, this is a milliliter, not meters. So 1 times 10 to the minus 3 liters is 1 milliliter. Cancels the milliliters, using with an answer in liters. I know that 1 million liters is 1 megaliter. And so if I do that happy math, 7809 times 1 second EE negative 3 times, not times, divided by 1, 2, 3, 4, 5, 6. And that gives me 7.809 times 10 to the minus 6 microliters. And just from a pure smell test, I look at that and I say, okay, is it reasonable to have a very, very small number of milliliters in a megaliter? Yes, absolutely it is. Because that's why we deal with this, is to work with those different numbers and put them in ways that make sense. Okay, so that makes a lot of sense to me. Sorry, I swear that I slept. Now I'm going to skip to the second part. We're going to start talking about how many significant figures are in each of the following measurements. I'm going to do all of these. So I'm going to look at this number right here, this 2960, right? And we need to determine how many of these zeros are significant. Now, I know that this first 0 is just a placeholder. These 2 zeros are also just placeholders. But this one at the end is significant, because I wouldn't have written it if it wasn't significant. So I count 1, 2, 3, 4 sig figs there. And the other thing that I can do is I can enter 0.002960 on my calculator. And then I can say mode, scientific, and then quit that. And then enter that again, and that gives me 2.96 times 10 to the minus 3, right? And it's that 2.960 times 10 to the minus 3 tells me that 0 at the end is significant, but the ones in the front are not, because they go away once I put it into scientific notation. Now, my calculator has dropped that last one, but I know that it's significant because of where it is in that number. Okay, so that last 0 is significant. All right. Now, when we look at the next number, and I look at this and I say, okay, how many sig figs do I have? Well, these zeros are significant if they're between a 1 and the decimal place. Okay, so they can be, they cannot be. So we could, knowing that there's a decimal place there, that would be 4 sig figs. That indicates that all of those zeros are significant. Now that I have 2 on the opposite side, on the other side of the decimal place, I know that those 2 are significant as well, because I wouldn't have bothered to write them if they weren't significant. So I had the 4, now I have 2, that gives me 6. Okay. If we look at this number, however, there's no decimal place in this number. And so if I were to put that into scientific notation, the only number that's going to be left is this 1. So that is 1 significant digit, because we don't know how accurate that number is. It may be a guesstimate. And so we may only have that 1 sig fig. Since we haven't been given a decimal place anywhere, we have no idea. Okay. Excuse me, sorry. So on this one, I look at this number, 1.000. Again, all of those numbers to the right of the decimal place, since they're written, are significant. That means that this one has 4 sig figs. And when I look at this last one, both the 0 between the 2 and the 9, that one is significant. And the one after the 8 is significant, because I wouldn't have written it if it wasn't. So 1, 2, 3, 4, 5, 6. So that's how I get those. Now, the next part that we're going to come to is actually doing some math with these numbers. And this is when sig figs become a really big deal, because we have to know how many sig figs are in each of these things that we're dealing with when we do the math. Okay, so the first thing I have to do in this math, I'm so sorry. I swear if I turn that camera off, it will stop. The first thing we have to do is what's in the parentheses. So I need to do the addition for 200.5 plus 2.59. Now that's the math I'm going to do. And I go ahead and do that math with my calculator. And I know that when I do this, I end up with 203.0. Okay, so that's the number that my calculator spits out. The question becomes, is that number really as significant as that? And the reason that I say that is because I have a different number of decimal places in these 2 numbers. So when we do addition and subtraction, our number of sig figs is based on which is the least well known. So the 200.5 has less sig figs in it past the decimal place than this one does, 2.59. So our answer has to end right here in that first decimal place, which means that I have to round this up, which gives me 203.1. Right, so that's the number that I would come up with for that. I then have to take that 203.1 and multiply it times the 60.7. Now, when we do calculations, we don't actually want that rounded number to be what we use to do the calculation. We want to use the number before it's rounded. Okay? So I'm going to leave the 203.09 in my calculator. Multiply that times 60.7. The reason that I did this is to show you that this should only have 4 sig figs and not 5. Okay, it should only be 4 significant digits. Now I do that multiplication times the 60, and that gives me this answer. 12327.563 is the number that I spit out of my calculator. But looking at this, I see that there are 3 significant digits here and 4 significant digits there. And so my answer should only have 3 significant digits. There are 2 ways that I can handle it. One, I can put it into scientific notation. And so if I put this into scientific notation, that gives me 1.3, sorry, I forgot my 2, 1.23 times 10 to the 4th. And that is 3 significant digits there. So that's cool. The other thing that I can do is I can say it's 1, 2, 3, 0, 0. Because those zeros at the end are not significant because I have not put a decimal place there. They're just placeholders. So either one of those answers is technically correct. Now, looking at my units, when I do this addition, this is meters. Meters times meters gives me meters squared. So it doesn't matter which answer I decide to report, they need to be in units of meters squared. Okay, so we need to make sure that we're aware of how many decimal places we should have, even though we don't want to do the rounding with the number that we're calculating with. We need to know what it would look like if it were being reported there. Okay, because that helps us determine how many sig figs we should be dealing with. It is important that you think about that as you go through these steps. How many sig figs should that answer have? Because that may affect what you're doing. Okay. So sorry. Okay. So the next one that we do is 3.3 times 10 to the minus 4th divided by 9.9 times 10 to the minus 5th. Now, both those numbers have 2 significant digits. So I put my 3.3 second EE negative 4 divided by 9.9 second EE negative 5. And the answer that I get out of that is 3.33333, and it has no decimal places to it. So my answer is 3.3, and that's grams per milliliter. Because again, this is grams, this is milliliters, so it's grams per milliliter. Okay. I have my 1.0 times 10 to the 5th times 15.0. Now I'm going to do that math. 1.0 second EE 5 times 15.0. And I get 1.5 e to the 6th. And the question becomes, how many decimal places should that be? Well, this number right here has 3. This one has 2. So it should be 2 sig figs. And actually the answer that I got, 1.5 times 10 to the minus times 10 to the 6th, which is going to be meters because I took seconds times meter per second, gives me meters. That is the correct number of sig figs and the correct units for that particular answer. Let's take a look at the next one. 25.8 divided by 2.00. Now, I do this math, and I get 1.29 times 10 to the 1st. This is grams per milliliter. So since I'm dividing, I end up with milliliters as my answer. And it makes sense that it's 3 sig figs because there are 3 here and 3 here. So the answer should be 3 sig figs as well. Okay. This could also be listed as 1290. No, that's entirely up to you. Just make sure it's only 3 sig figs. Now this one, 153.6789 minus the 42.3409. Let's put that in our calculator as written. 153.6789. I'm going to subtract 42.3409. And I end up with this number that spits out 1.11338 times 10 to the 2. And I look at that and I say, okay, I don't know that I like that. So let's get rid of the scientific notation. And so that would come out as 111.338. But then I look at my numbers, and I have 4 decimal places here and 4 decimal places here. So that answer, this answer, needs to have 4 decimal places. So I need to write a 0 at the end of that, because it still needs to be that significant. So we need to put in that 0 there. And it was grams minus grams, so that's still grams. Okay, so that's how we do that there. Need to check something in a second. Okay, sorry, got an email, had to read. All right, let's take a look at our temperature conversions. So it says room temperature is about 25 degrees C. What is the temperature in units of Kelvin? So I need to know what the conversion is. So I come over here and I see that there are temperature conversions here. And TF stands for Fahrenheit, temperature in Fahrenheit. TK is temperature in Kelvin, and TC is temperature in Celsius. I'm looking for TK. I want to calculate TK from TC, because this is a TK that I want, and this is a TC that I have. So the equation that I need is temperature in Kelvin is equal to the temperature in Celsius plus 273.15. Okay, so that's the conversion that I'm going to do. And so I plug in my TC, and that's equal to 25 plus 273.15. 25 plus 273.15. And that gives me an answer of 298.15. Now, if I want to do additional math with it, I'll leave it as 298.15. But from a technical standpoint, because this number is only known to that ones place, then I would report this as 298K. Okay, it's a fairly common thing for us to see. The temperature at which carbon dioxide sublimes is about 195 Kelvin. What is the temperature in units of degrees Celsius? So I'm again doing Kelvin and Celsius, and now I'm going the other direction. I want the TC from TK. And so TC equals TK minus 273. And so my Kelvin temperature is 195 minus the 273.15. 195 minus 273.15 gives me negative 78 Celsius, and that's degrees C. Okay. What is Celsius? And it is degrees C. Which of the following temperatures are possible? 0 Kelvin is the lowest possible temperature that can be obtained. Okay, so 4,000 Kelvin looks okay to me. Oh, that's 4,000 degrees C, and 4,000 Kelvin both look okay to me. And look at this one. That's a negative Kelvin. I'm not okay with that. So I don't think that works. The negative 200 degrees C. So 273.15 plus negative 200 makes that a positive. So this is this one is okay. And if I take my 273.15 and I add a negative 400, I get a negative 126. I really don't like that negative 200 Kelvin. So that's the one that I would say is the one I would report. Now, from a technical standpoint, I have 2. That is correct. So, because that negative 400 plus 273 is still a negative Kelvin. So that does not make sense. Neither one of these do. But this is technically the one that I would call out first because it's a negative Kelvin. Okay. This one I'd have to do math to figure out. So both of these would be the ones that I would indicate. Okay. All right. Let's talk about some unit conversions. So convert 10 miles per hour to meters per second. Use the conversion factors given in the text. So I'm going to refer you here. So 10 miles per hour. I have 10 miles per hour. That's my initial unit. I know that 1 mile, which is an MI, which is why I said that, 1 mile is 1.61 kilometers. Okay. Now, if I can get to kilometers, then I should be able to get to meters, right? So I know that 1 mile, 1.61 km, 1,000 meters equals 1 km. That's from the table up here. Okay. So remember that km is 10 to the third. So that's where that comes from. And then if I want to go from hours to seconds, that time is not actually on here. And the reason for that is I'm assuming that you know how many seconds are in a minute, how many minutes are in an hour. So I'm hoping that you can do that. Now, I would not do this as one conversion. I would say, okay, there are 60 seconds in 1 minute, and then 60 minutes in 1 hour. So since this is hours, I have a choice. It doesn't matter which one I work with first. I can do the miles or I can do the hours. I'm going to work with the miles just because I tend to work top to bottom. It's just how I tend to do things. So if I know I'm in miles and I want to get to meters, I need to go through kilometers based on this number that I have here. So I put my 1 mile on the bottom because that cancels the mile. And then I have my 1.61 km on the top. If I were to do that happy math, I get an answer that would have kilometers per hour, which is not meters per second. So I know I'm not done. So now I'm going to go from kilometers to meters. So I know that 1 km is 1,000 meters. KM's cancel. So if I were to stop here, I'd have meters per hour, which is again not what I'm looking for. So I want to get rid of that hour. So I put the 1 hour on the top. And that's 60 minutes that I put on the bottom, because that's the conversion factor there. So it cancels the hour. And now if I did it, I'd have meters per minute. Not quite there. Almost there, but not quite. So I know that 1 minute for this is 60 seconds. And if I do that, my minutes cancel, and that leaves me with an answer that's in meters per second, which is what I was looking for. And so if I do this happy math, 10 times 1.61 times 1,000 divided by 60 is 4.47. And looking at all of these numbers, our conversion factors are considered infinitely known. So we don't use them to determine how many sig figs we should have. It means the only thing I consider is the 10.0 that I started with. So it should be 3 sig figs. So it's 4.47 meters per second. Okay. So I can do my unit conversions in many, many different ways. It doesn't really matter how I do them as long as I end up with the units that I want. And if I haven't gotten to the units that I want, I'm not done yet. Okay. So I can do this any way I need to. Let's talk about the next one. So convert 5.0 centimeters cubed, 5.0 centimeters cubed to liters. Okay, that's a fun one. And that requires that I know a couple of things that I may or may not actually know. So right here, it says that 1 cubic centimeter, 1 centimeter cubed, equals 1 milliliter. So 1 centimeter cubed equals 1 milliliter. And I know that there are 1,000 milliliters in 1 liter. Okay. Or I know that 1 liter, 1 milliliter is equal to 10 to the minus 3 liters. Okay, so I can use those to work with this, right? I'm going to take my 1 centimeter cubed, it's 1 milliliter, and that means that I'm now in milliliters. And I know that 1 milliliter is 1 times 10 to the minus 3 liters. And so 5 times 1 second EE negative 3, 0.005 liters. Okay. Awesome. Well, that's fun. Now I want to convert 3 centimeters cubed to millimeters cubed. And it says to watch the cube units. Okay. So I'm going to start with this number, 3.0 centimeters cubed. I don't know any relationships. There's nothing on here about centimeters cubed and meters cubed, but I do know that 1 centimeter equals 10 to the minus 2 meters, and 1 millimeter is 10 to the minus 3 meters. So I know that 1 centimeter is 10 to the minus 2 meters, and 1 millimeter equals 10 to the minus 3 meters. And I can actually use that to get to where I need to be. Now remember, I need to set this up so that the centimeters cubed will cancel to give me meters. So I know that 1 centimeter, 1 cm is equal to 1 times 10 to the minus 2 meters. And then I need to cube both of those. So we end up cubing both those numbers to get that unit to cancel. And that means that I'm going to have to cube the 1 times 10 to the minus 2. Okay. That gets me to meters cubed. And I know that if I want to get to millimeters, 1 millimeter equal 1 times 10 to the minus 3 meters. And again, I need to cube this, and I need to cube that. So I'm going to take my 3.0, I'm going to multiply that 1 times 10 to the negative 2, and I'm going to cube that. And then I'm going to divide by 1 second E negative 3, again, cubed. And that gives me 3,000. Okay, so that's what I'm looking at there. So we can work with those things. We just need to remember that we have to cube the numbers as well as the units. Given that the density of olive oil is 0.92 grams per milliliter, calculate the following. The mass of 20 milliliters of olive oil and the volume of 20 grams of olive oil. Okay, I always start with what they give. So they've given me 20 milliliters. And I want to get out of milliliters and into mass, which is grams. So based on this number that I have 0.92 grams per milliliter. So that cancels the milliliters and leaves me in grams. So I take my 0.92, I multiply it by 20, and that gives me 18.4. Now, from a technical standpoint, the number that you've been given is 3 sig figs. And if this was an actual conversion factor, we would consider this infinitely significant. But we know that the density, grams per milliliter, is a calculated value. It's not a definition. So this being 2 sig figs means that my answer should be 2 sig figs. So I would report that as 18 grams. Okay. Now, if I want to do the volume of 20 grams, I start with the 20.0 grams. And I know I'm going to use that same conversion factor. The question becomes, how am I going to use it? Well, I multiplied by it last time, so I'm probably going to divide this time. And I am 0.92 grams in 1 milliliter. And the grams cancel. So that'll give me the answer that I want. And then when I do that math, two significant digits, I get 22 milliliters. It's 21.73, and I have to round that up to 2 sig figs. Okay. So that's done. Which of the following metals will occupy the largest volume per gram of metal? Hint, is this asking for the least dense or the most dense? Now that is a hint, and if that helps you, that's great. It doesn't really help me. It says, which of the following metals will occupy the largest volume per gram of metal? Okay, it says per gram. So I'm going to say, okay, if I have 1 gram of each material, I take that 1 gram and I divide it by that, the density that I'm given, 19.3 grams per centimeter cubed. That would give me the volume in centimeters cubed. So I'm going to divide 1 gram by each of these densities. Okay. When I do that, 1 divided by 19.3, 0.0, those are not significant. 5, 1, 8. And that's centimeters cubed. If I do that for this one, just answer over here. 1 divided by the 13.55. It gives me 0.0738 centimeters cubed. And 1 divided by 11.3 gives me 0.0885 centimeters cubed. So obviously I'm looking for the least dense material, which is this one right here, because that's the one that gave me the greatest volume. Okay. So even if you don't understand the hint, you can still do this by looking for which one gives you the biggest number in terms of the volume. What is the difference between accuracy and precision? Okay. So accuracy and precision. Let me find the chapter 1 notes. Let's see if it's in the review. I can't remember if it should be. Hello. Not signed in. I hate it when that happens. I did not. Oh my. Okay, let me open the other one. This is the lovely diagram that I referred to when we talked about this in class. So accuracy versus precision. So precision implies that we're getting the same number every time we measure it. Accuracy implies that we're getting the actual value that we're supposed to be getting. Okay, so accurate means actual value. Precision means they're close to each other. So the way that I would talk about this, let me say, accurate is that real value, and precision, how close measurements are to each other. If your car uses 22 miles per gallon and you go on a 400-mile road trip, how much gas do you need? If your tank is 16 gallons, how many times do you have to fill up? If gas costs $3.27 a gallon, how much do you spend on gas, assuming you bought just enough to reach your destination? Okay. So the first thing I look at is 22 miles per gallon, and I write that down. And I'm actually going to put it up here. 400-mile road trip, 16-gallon tank, and $3.27 per gallon. Now, all I've done is pull all of the numbers out of that question. I like to pull them out because then I don't have to read the whole thing. How much gas do I need for a 400-mile road trip? So if I'm traveling 400 miles, and my car can travel 22 miles per gallon, then that tells me how many gallons I will need to be able to make this. 400 divided by 22 gives me 18.18. Now, looking at those numbers, I think we're going to call 22 the most precisely known. 400 we can guesstimate as all three being significant, so I'll call it 2 sig figs. So that would report 18 gallons. A tank is 16 gallons. I need to get 2 tanks of gas because I take the 18 divided by 16, and it tells me that I need 1.1 tanks. So that's how many times I have to get gas. Gas costs $3.27 per gallon, and I need 18 gallons. It's $3.27 per gallon. And I assume that I'm only filling enough to get how far I need to go. Then that's going to be $59 to 2 sig figs. Okay. So that is the way that I would get to those numbers and how I would report them. I think this is the last page. Oh, no, it's not. It's the last page for this. So we're going to do this one and then we'll take a break. Package of aluminum foil contains 100 feet of product and weighs approximately 1 pound. Okay. So 100 feet squared and is 1 pound. The density is 2.70 grams per centimeter cubed. Find the approximate thickness of the aluminum foil in millimeters. And of course, it says that 1 pound is 4.53.6 grams. Okay. So I have 100 foot squared, and that's 1 pound. So I'm going to take this 2.70 grams per centimeter cubed. And I'm going to do a conversion. I want to get rid of the grams and get into pounds. So I'm going to divide by the 453.6 grams in 1 pound. And that tells me that it's 0.00595, 3 sig figs here, so 3 sig figs that I'm reporting, pounds per centimeter cubed. Okay. All right, pounds per centimeter cubed. Find the approximate thickness. Now I know that this thing that I'm working with is 1 pound. So 1 lb. I divide that by this conversion factor that I just got, 0.00595 lb per centimeters cubed. Okay. I'm doing that because I don't really know what else to do, right? But that gets rid of my pounds and gets me into centimeters cubed. If I'm looking for a thickness, that's a measurement in terms of distance. So at least I'm getting to a distance. And for me, that's closer. So I take 1 divided by this number that I just calculated, and that tells me that I have 168 centimeters cubed. Okay, so that's how many centimeters cubed this thing actually is. The other thing that I know is that the aluminum package of foil contains 1,000 feet squared. Okay, so I want to go from feet to centimeters. And I can do that because I know that 1 foot equals 0.305 meters, right? So if I take my 100 foot cubed and I take my 1 foot, it's 0.305 meters, and I cube this and I cube that, then 100 times 0.305 cubed tells me that I have 2.8372625 meters cubed. Now, since I'm in centimeters cubed over here, I'm actually going to erase this. Sorry. Since this is centimeters cubed, I'm going to erase this and go for meters cubed. So 1 meter is 100 centimeters. I'm going to cube this. I'm going to cube that. So meter cube will cancel, and that'll give you an answer in centimeters cubed. So 100 times 0.305 cubed times 100. And times 100 cubed. And that tells me that I have 2,837,262.5 centimeters cubed. Done. I cubed it. Darn it. So I made a mistake. I apologize. I did make a mistake. And that's because I put this as cubed and not squared. So I need to back this out. And that means I'm going to erase all of this. And I'm sorry about that. But it does happen. You know, I mean, as many times as I've done this problem, and trust me, I've done it a few times, I always fail to remember some things about how to do it. One of the things that you may notice is that I'm trying to work with the units, because if I work with the units, then that gets me, okay, if I know it's supposed to be this unit, then my math is supposed to be set up right, okay? So 100 feet squared, 1 foot is 0.305 meters. I'm going to square that and square that. And then 1 meter is 100 centimeters. And I'll square that. I'll square that. That will make a lot more sense. But rather than cubing everything, I need to square them. And that tells me that I have 93,025 centimeters squared. Now that makes sense to me, because since they're not the same unit, now I know what to do. Okay, I have 168 centimeters cubed that we calculated based on mass, right? So 168 centimeters cubed. And if I divide that by the 93,025 centimeters squared from the size of this thing, 93,025 centimeters squared, then that answer is going to be in centimeters. Okay, that's close. So 168 divided by this number that I just calculated. And that tells me that I have 0.0018059661 centimeters of that material. And they wanted me to report it in millimeters. Okay. So 0.0018059661 centimeters. I know there's 100 centimeters in a meter, and that 1 meter is 1,000 millimeters. Divide that by 100, times that by 1,000, and that gives me 0.0181. 3 sig figs that I had here, so I'm going with 3 sig figs down here. No. Now, did it seem like I wandered all over the place? Yeah, it probably did. But that's one of the things that I do when I solve these problems, is I don't always know exactly where to go, but I know, okay, I'm here, I'm not where I want to be. Let me try this. Let me try this. You know, and I mean, granted, that's going to depend on how much time I have. Absolutely it is. This is why I want you to practice as much as you can before you get to the test. Now, I'm going to stop at this point and give us a break here. I will pick up with a new video on page 3. We'll do pages 3 and 4, probably. Depends on how long it takes. So I will pick up there in a few minutes. Thanks, guys.